I got it.
Okay, so now I got to go back to here, back to here. All right. Wow. All right. Think.
Yeah. Okay, so now Pat, I'm going to ask Pat to come up to introduce our speaker.
Hello, everyone, and welcome, and a happy 2023 to you. During the pandemic days, this evening's guest, Paul O'Connor, gave a wonderful lecture from Brookhaven. Tonight, Paul has come to the Pace campus to help kick off the new year. Paul is at the forefront in creating ideas for instruments which will better yield answers to the elusive origins of our vast universe. This, along with the update on the Large Synoptic Survey Telescope, known as the Vera Rubin Observatory, will be the subject of his lecture. Please give a warm welcome to Paul.
See if the jury rig manage that. Okay. I need to stop sharing this. Share. Let me see if I can get my. Except I can't find. Here. You just do there. And good, I said it.
Security alert.
Okay, thank you. Well, good evening, everybody. Thanks for inviting me. I appreciate the opportunity to talk to you in your kickoff of the 2023 season. Like Pat told you, I work at Brookhaven National Lab. I'm an instrumentation developer, and tonight I want to talk to you about some developments that we're involved in to try and answer some provocative questions that are facing us in observational cosmology. And a big shout out to Steve Bellavia, who's worked with me on many of these programs and does a great job with the amateurs on Long Island, and is overall very inspirational with his travel logs. So Steve, I know you're out there.
Thanks, Paul. It's been a pleasure working with you.
All right. So let's just dive in. Cosmology, what is it? The study of the universe as a whole in all of its vastness. And it asks questions like, what's in it? How did they get there? How have things evolved to the state that we observe them in now? Also, from an academic standpoint, it's a little bit unusual because unlike pretty much any other discipline, it can be considered belonging to the humanities, right? So it's a branch of metaphysics as well as the natural sciences. Of course, tonight we're going to stick with the natural sciences, the physical cosmology side of things, but there are some interplays between the two. And at the outset, I want to give you the idea that this cosmology in the 21st century is undergoing a scientific revolution, which is the synthesis of general relativity, that's Einstein's theory of the nature of space and time, and combined with precision measurements that are coming from new telescope technologies that have given us a completely new understanding of the nature of space and time, and have given us a discovery of previously unknown, I'll call them substances for now, dark matter and dark energy, which turn out to dominate the contents and evolution of the universe. So simple story. So probably most of you are familiar, this Big Bang model is the pillar of modern cosmology. Things started about 13.8 billion years ago in a primordial singularity, and since then it's been expanding and cooling from this very hot and very dense state. It was proposed in the early part of the last century based on solutions, possible solutions to Einstein's general relativity, and then subsequent measurements have confirmed this theory. It was sort of tussling with the steady state theory of Boyle back in the 19 teens, 1920s, 1930s, but it's now come to be known that this is correct theory. It's experimentally verified by a number of different observations. Until the end of the 1990s, there were big difficulties in reconciling some of the observed properties of matter and energy in the universe with the theory. But as these new instrumental capabilities came to being, there were two major discoveries which kind of sewed up all of these dissonances into one, what we now call the standard model of cosmology, sometimes called lambda CDM, which stands for a dark cosmological constant and cold dark matter. So it's now known that most of the matter in the universe is not the kind that we see that makes up our world. That's known to terrestrial physics. It's so-called dark matter, doesn't interact with normal matter, doesn't interact with electromagnetic radiation, can't see it. And secondly, that the expansion rate of the universe began to increase about 7 billion years ago, about halfway back to the Big Bang. And we use the term dark energy to refer to that. These are some of those technological advances that made this all possible, right? So first of all, the ability to cast large glass to figure and code it was let's say the first half of the 1900s. Then in the second half of the 1900s, we had the switch from observing with the naked eye or with photographic film to electronic detectors, silicon charge coupled devices. These have, just to give you an idea of how much of an improvement this was, not only do they have, say, about 100 times the sensitivity to light, this is the optical spectrum on the horizontal axis, and this is a log scale of sensitivity, right? So red is the modern detector. So much better than photographic film, far better than the naked eye, despite the fact that so many discoveries came from pre-CCD era. But in addition, it's sensitive out to wavelengths much farther into the red, into the near infrared, before dropping off. So this was a big, big advance. And of course, it made possible things like space telescopes, which couldn't really have effectively used film, although there were spy satellites that actually did record images of Soviet Union and other places on film canisters and drop them back out of orbit and had them fetched by aircraft. It's a remarkable story, actually, the Corona spy satellites in the early part of the space age. Of course, now these charge coupled devices provide a digital recording of image data, and you can beam it back to Earth with your telemetry link. Radio astronomy played another big part in this cosmology model coming together. Maybe you recognize the Holmdel Horn antenna. This is Bell Labs radio antenna, which they were using to conduct experiments on microwave transmission of telephony by bouncing it off the Echo satellite, which is basically just a big silvered balloon. And in studying the noise properties of this, they inadvertently discovered the cosmic microwave background, which plays a big role and has become the subject of a whole class of instruments. All right, so how do we know there's dark matter? This is a story that has a few parts, but they all come down to the same. So Zwicky in the 30s observed the constituent galaxies of the Coma cluster, which probably you amateurs have also looked at, and measured the velocities of these swarm of galaxies that are bound together gravitationally in Coma. And then in the 50s through the 70s, Vera Rubin, for whom our observatory is named, looked at the rotation rate of galaxies, the rotation curve, which is how fast things are moving as a function of radius from the center, and found that they're spinning much differently than would be expected. Finally, this is gravitational lensing that you're seeing on the right. These banana-shaped little smudges, the cigar-shaped smudges, are the images of galaxies that are in the back of this Abel cluster, and the gravitational potential of this compact cluster is able to bend the light. This is another aspect of Einstein's theory. It bends the light that passes through that cluster on its way to us and distorts things in this characteristic tangential shape. What all of these images and studies have in common is that they have found that there's a source of gravitational energy or gravitational potential, which can in no way be accounted for if you sum up all the mass in the stars, the constituents, or the galaxies. So something is providing additional gravitational energy. It's been backed up by many more detailed studies since then. As one astronomer put it, evidence for dark matter is hitting us over the head everywhere in the universe. So to tell you a little bit about the evidence for dark energy, which is a whole different thing, first, I want to remind you of how astronomers measure the distance to things that are very far away. For example, say we want to observe a galaxy or other extragalactic object that's 6 times 10 to the 21 miles away from us. That's a long way. And we know that light travels at a finite velocity, which I've described here as 670 million miles per hour. And so the light that we see from that galaxy at that distance was emitted 1 billion years ago. So, I cheated. I picked this number because that's equivalent to 1 billion light years. The light year is the measure of distance. That makes more sense. And so when we see something far away, we're seeing it as it was sometime in the past. And at cosmological distances, that's a long time in the past. The other thing to remember is that Hubble's law says everything is, as the universe expands, everything is receding from everything else. There's no center, right? But everyone perceives themselves to be at the center of everything else separating from them. And the separation velocity is proportional to the distance away. So it turns out at this billion light year distance, that galaxy is, or when it emitted that light, it was receding from us at 48 million miles an hour, pretty fast. The problem is that all these characteristic metrics are unmeasurable. They're not directly measurable. You can't put a tape measure out to this kind of distance. There are techniques to measure distance at much closer range, up to a few million light years, but not billions. We can't start a stopwatch when the photon leaves that galaxy and stop it when it gets here. We don't know when that happened. We can't put a speedometer on the galaxy to measure how fast it's receding from us. Instead, astronomers use redshift. You may be familiar with this term. What it is that as light travels through expanding space from a receding object to our telescope, its wavelength is shifted into the red. So this is called redshift. It is similar to, but not the same as a Doppler shift, which is what's used when you hear a train whistle coming at you. It's higher pitch coming at you and lower pitch going away. And it's how your friendly highway patrolman radar gun tells him how fast you're approaching, how fast you're going. At this distance, or at this time separation, it turns out that the light from the distant galaxy is received 7.5% redder than it was emitted at. So the expansion of space kind of stretches these light wave vibrations out. And we use the term redshift is given the symbol Z, and it is precisely equal to how much redder things got. So this galaxy, so a billion light years, an object at a billion light years, so things are redder by 7.5%. Now, you might ask, how do we know what color it was when it was emitted? Typically, this is done using spectral lines. So spectral lines are emitted by transitions in atoms and molecules that are well known, and things that emit those that light, those spectral lines in galaxies are the same then as they are now. So we can measure that spectral line and how much it changed, and we can detect the redshift. So this is a very powerful technique. And graph over here. This is that relationship. How far you're looking back in time, out to the time of the Big Bang, which is the vertical red line, and how much redder an object. All right. How does this relate to dark energy? So in the 1990s, teams of astronomers wanted to measure the change in the expansion rate of the universe. The universe expands, but it's full of matter. Matter gravitates, and that gravitational attraction is expected to slow the rate of expansion, right? Things are separating, but they're also pulling each other together. So they set out to measure what they call the deceleration parameter. What is the second derivative of the rate of change of distance, right? How much things are slowing. They did this by using standard candles, so-called, and standard rulers. Without going into detail, these are yardsticks for brightness measurements that are well known and can be calibrated out to large distances. And what they found, so they measured the number, but it came out with the opposite sign that was expected, right? So they found that these objects at over a certain range of time scale in cosmic time showed accelerated expansion, not decelerated expansion. And when they put that into simulation, so here on the right, if we get this video to play, I'm going to show you a simulation of a large volume of universe filled with initially diffuse and spread out, let's call them galaxies, or it could be just gases. Initially, they're uniformly distributed, a few statistical fluctuations here and there, which then grow with time as these structures self-gravitate into the matter grabs hold of itself, forms into these structures, and they form an interesting characteristic web-like, sponge-like pattern. And it turns out that when in this model, without dark energy, you would not get these patterns. These correspond to the patterns that are observed in the sky today. Without dark energy, these structures would have formed much earlier, right? Because the repulsive force of dark energy impedes this gravitational collapse. Gravitational collapse still goes on, but at a slower rate than it would. So dark energy is the name we give essentially to this accelerated expansion, but it can be equated to the energy content of a substance with a negative pressure, which is actually a part of Einstein's theory that was kind of on the sidelines until these discoveries. So here's how things look in the current picture. Remember, cosmology asks what's in it, how did it evolve? And kind of we know the answers now, quantitatively. According to this concordance model, we have a pie chart which is dominated by dark energy, with the second biggest component being dark matter, the ordinary matter that we consist of, that our cookies and oranges consist of, is a small slice of that pie. There's a little bit of neutrinos and a little bit of photons in there. But this is what the model is telling us, and you have a hard time arguing with the precision of these numbers. Prior to this time, cosmology was not a precise science at all. The instrumentation makes all the difference. And on the right is this is a nice NASA graphic. It shows evolution in time on the left, Bang on the right you have today, and the size of this tube or this horn is supposed to show the size of the universe. The radius of the universe is something that can be defined. And the problem here is that we've answered the question of cosmology in the broadest sense, but what is this dark matter? What is this dark energy? How come we're now seeing acceleration? And a concise way that this was presented that I like to show this slide. It's from this book by a collaboration of cartoonist and a theoretical physicist, which is called We Have No Idea. And this is basically what I just showed on the previous slide. Highly recommend to look at We Have No Idea, the book by Whiteson and Cham. It's got a lot of other interesting puzzles. I find it fascinating. So we've found out these answers, but it motivates experimentalists, observationalists, to ask, what can we do to study this, to find out what these substances are and what's going on? Make sense out of this puzzle, which seems to fit together so well in explaining what we observe, but leaves us clueless as to how does it fit into the rest of physics. None of these substances is part of terrestrial physics. So how about a new telescope? One that would make a three-dimensional mass map of the universe back to half its current age, which is the time at which dark energy became dominant. And you would want to do that by detecting as many galaxies as you could out to redshift 1. Redshift 1 is about that look-back time. By the way, the galaxies that we're seeing at these higher redshifts, they look nothing like the beautiful pictures that you see of the spirals and ellipticals and so on. At these distances, here's a picture taken by the Subaru telescope of a field of distant galaxies. They really just look like little smudges. They cover a few more pixels than stars, but not many. But you can classify these objects as to which are galaxies and which are stars. Of course, the stars are all in the foreground, part of our galaxy. The telescope that you want to perform this survey with must have a wide field of view, gobble up as much sky as possible, a large collecting area to see things that are very faint, wavelength coverage out basically from the ultraviolet into the near infrared, so you can get redshift tagged, and the ability to take short exposures and move around quickly from exposure to exposure to cover the whole visible sky. And 23 years ago, more or less, a couple of astrophysicists and telescope makers came together and proposed what was then called the Dark Matter Telescope for just this reason. It's an interesting design. It's a three-mirror design, which makes it physically compact, right? With three reflections, you fold up what would otherwise be the length of a telescope tube and into a compact thrust and frame, which will give it the ability to turn around quickly because you don't have a long moment arm as most telescopes do. So this dark matter telescope paper was the inspiration for what then became, after about 15 years of proposal writing and follow-up from these crude drawings, the Large Synoptic Survey Telescope, former name for what's now the Rubin Observatory. It's a dedicated facility. This photo was taken in about, I think, in 2019 when the observatory construction was about to be halted by COVID, Chile. Now the acronym stands for the Legacy Survey of Space and Time, whatever. It's got a 3.5-degree diameter field of view, which is quite big for a large professional telescope. It can take 1,000 images per night. It will have an image depth for a single 30-second visit to a level of faintness, which is about 100 million times fainter than the faintest star you can see with the naked eye. So it's really faint. So the mantra is, it's wide, fast, and deep. Is it the widest field of view telescope that exists? No, there are ones that have 4 and 5 degree fields of view. Is it the fastest? Not at all. There are astronomical cameras that can take 1,000 frames per second. Is it the deepest? Can it see the faintest thing? Certainly not. Even if you exclude space telescopes, the Subaru telescope on Achaia can get about 5 times deeper, a few tenths of a magnitude deeper. But this is the only instrument that can combine all of these characteristics. So it's a very ambitious program. It was finally approved for go-ahead, I guess, in 2014, but as I said, a lot of the work has been done already. It's being built by the National Science Foundation. Department of Energy is supplying the camera, which is our part of the observatory. And there are a number of private contributions and national contributions as well. So as I said, this is a view from 2019 or thereabouts. Oh, I'm sorry, one more thing. Sad to say, I showed this slide at my last lecture, and as with many mega projects, cost and schedule numbers are a moving target. COVID didn't help in this case, so we're now getting up to the $1 billion level, and fingers crossed, early 2025, science operations will start. Hopefully, we get some early engineering images for that, say mid next year. Okay, so now the dome is finished, the structure is completed, and there's a telescope in it. This is the telescope mount assembly. Looks just like the pictures, right? It has neither the camera in this location here at the top end, nor the mirror, but it does have mass simulators for both of those. So this is the whole thing. This is the thing. It weighs about 300 or 400 tons. I don't remember the exact number. It's heavy. But as we can see in a real-time video that was taken just a couple of months ago, that's how fast it moves. This is real time. And notice the azimuth and altitude are both slowing here. And you would be hard-pressed to find a professional observatory telescope that can slew 20 times slower than this. Right? So I was really impressed when I saw this video. They got this machine working, and it's going to be awesome. It has to have this speed because the idea is to take a 30-second picture of part of the sky, move to the next part of the sky, take another picture, and while it's moving, the shutter's closed, you're dropping photons on the floor, so you don't want that. Okay. Okay. All right, so big glass, like I said, is part of the key to these big new machines. This is the main mirror. It was shipped to Chile. As I said, it's not on the telescope mount assembly yet. It's still in a shipping container. It was quite a task to bring this thing from the mirror lab at the University of Arizona up the mountain road, 50 kilometers of basically dirt road, get it up there in one piece. The secondary is shown here. It's not coated yet. It's 3.5 meters in diameter, bigger than most professional observatory telescopes. And the first of 3 corrector lenses for the camera is, I'm told, is the largest lens ever made. So they could kind of walk through it. The focal plane is the part that we built. So this is a picture of what it looks like. This is at SLAC National Laboratory, our sister lab and partner in Rubin. These reflective stuff you see up there is 3.2 gigapixels worth of CCDs. There are 189 of those CCDs in this focal plane. It's paved with silicon. And because this is a very low F number, it's a f1.2 telescope, the depth of focus is really small. So this giant mosaic of 200 pieces has to conform to a plane that is where no part of the imaging surfaces are more than, let's say, 1/10 of a human hair from the ideal geometric plane. Because it's so big and its readout is so highly parallelized, there's 3,024 channels that all disgorge the image data at once. We chose to make them in modules. So this is one of those modules, like about the size of a bread box. We call it a raft. And the raft has 9 16 megapixel CCDs on it, each raft, precisely aligned and supported by thermal and electrical support in the box that lies below it. Extremely precise mechanical. We built 25 of these at Brookhaven, shipped them over to our partners, who then installed them in the focal plane, which is a cryostat. These things need to be kept cold in order to have their sensitivity. So this thing is going to have a first or a third corrector lens forms the vacuum seal, and then it's going to be pumped down to evacuate it, cooled to -100. The electronics generates about 1 kilowatt of heat, and that all has to come out of this cryostat. Kind of tricky. And so what we've done with this after it was all built is we used this camera to take a picture of Vera Rubin herself, studying with a densitometer a picture that she in turn took of some of these galaxies to elucidate their rotation curves. So I like this image, and it also helped us to evaluate how well the camera is working. And you can see there's a tiny little black sliver here. We have, out of the 3,024 channels, I think we have 1, 2, 3 that are not currently functioning, but that's well within the specification, and it's kind of remarkable for any camera, let alone one with so many independent readouts. Okay, I don't know if I can get this video to play. This is on the internet, and I was planning to put in a lot more graphics, but CNET does a much better job. Doesn't look like I have playable video here. But I encourage you to go and take a look. This is a trip to the camera lab at SLAC. That was, maybe I can get this after we finish. Play on the machine here. Very well narrated, shows the camera in great detail, shows it moving on its assembly station and so on. Highly recommended. So we finished our part of the construction of the Rubin Observatory. We're, of course, looking anxiously forward to seeing the data come out of it. That's mostly in another department. We as instrument builders are decided to start thinking about what could come next after this remarkable optical telescope. We get plans in place. As you saw, it's been almost 25 years that the dark matter telescope been brought to reality. So it's not too early to start thinking about what will come next. This Rubin will operate for 10 years starting in 2025. So by 2035, we want to think about having something new ready. The problem is, if you have a telescope on the Earth and it's an optical telescope, it have a lot of problems trying to find sources at redshift greater than 3. Not because they're too faint, because they're too red. So this redshift makes them red. And 2 things work against us here. First is the atmosphere. The atmosphere is not our friend. This graph on the bottom shows the transparency of the atmosphere. I don't know if it's at sea level or at mountaintop height, whatever. The arrow shows the band of wavelengths corresponding to redshift 0 to redshift 6. We'd like to try to see out to redshift 6. And you can see that once you get much past redshift 3, you've got all these absorption lines. The atmosphere becomes nearly opaque, awfully difficult to observe through that atmosphere. And even if you could get rid of the atmosphere, you have another problem. The problem is that the CCDs, which are the backbone of electronic image recorders, don't absorb light at these long wavelengths. Silicon becomes transparent. So it's kind of the opposite problem. The atmosphere is transparent in the blue, and it's opaque in the red. Silicon is opaque in the blue, which means those photons are absorbed, converted to electronic charge, and read out by our converters. But it's transparent in the red. We don't have any sensitivity. In order to go to longer wavelengths, you have to use some exotic semiconductors that really can't be processed into these sophisticated nanostructural patterns that are needed to make a CCD. So where do we go from here? Well, we and others are thinking about moving out of the optical domain altogether and building a radio telescope, a survey telescope in the radio frequency bands that can observe what's well known to radio astronomers, 21 centimeter line of neutral hydrogen. So hydrogen is a simple atom. It's got one proton and one electron. They each have spins. The spins can be parallel or anti-parallel. To make the switch from parallel to anti-parallel, there's a quantum transition involved, which results in the emission of a photon, we can say, but it's not, doesn't look much like a photon, an electromagnetic wave with a wavelength of 21 centimeters and corresponding to a frequency of 1.4 gigahertz. So why would we make a hydrogen telescope? And by the way, this image, one that Steve put together for me, showing, I forget which galaxy this, or galaxy, small galaxy cluster, you can see the visible light image. You see these satellite galaxies. They look like they're standing off by themselves, but when you see it in 21 centimeter light, you can see that there's a lot of interaction going on. This is something that is really useful in the nearby universe. We're interested in the really far universe. So here I've shown the atmospheric transparency out beyond the graph I showed before, which just covered the optical range, where starlight is redshifted into this horrible region above 1 micron. But in the radio, 21 centimeter light with redshifts from 0 to 6 happens to be in a radio window which is almost entirely transparent, which is great. Moreover, this 21 centimeter line is very, very sharp. So it has like 100 parts per million of frequency width. You remember, you're picking this up with a radio receiver, not what we think of as a telescope. And we're building a spectrometer, not so much an imager. So this means that when we see a sharp line from a distant object, and we can figure out that it's coming from 21 centimeter hydrogen by measuring its wavelength at our rest frame, we can unambiguously tag the redshift very precisely. So it's a great machine for looking out at redshift past 3 and finding out where things are. And there are a couple of ways that you can play the game. In my last talk, I talked about a proposal that we put together and a sort of demonstrator pathfinder that we realized with a whole bunch of student labor and a whole lot of volunteers on the BNL campus. So these are interferometers. This proposal is for a gigantic one that would be comparable to the mega project. It might be suitable as a next generation survey instrument for cosmology. It would be 32,000 low-cost parabolic dishes, closely packed, frequency range that corresponds to this redshift range, which, by the way, is still considered the modern universe here. It's where dark energy got started. This got a long way to, this is kind of a picture that corresponds to that 2000 picture of the dark matter telescope. It'll have to evolve a lot more, and it'll have to be shown to be feasible. To do that, we started a Pathfinder program. We built this 4-dish interferometer on the BNL campus. Both of these instruments are interferometers. So the way an interferometer works, a collection of receivers put together over an area can be made to act like a lens of that diameter, the diameter of the array, not the individual dishes. Pardon me. And that's what gives us the angular resolution. By playing a few other tricks, you can convert this into an image. You can make maps. So we hope that something like this could make a map of those filaments that you saw in the simulation. And VMX has been working now for over 5 years. We've got a huge data set. It runs autonomously. If we had a few more people on the team, we hope to show that the hydrogen that we see with BMX can be correlated against optical galaxy surveys, which exist in this narrow redshift range that we're sensitive here, and basically confirm that this technique is going to work. But I'm not going to say any more about interferometers. What I'm here to mainly, oh, except for one thing. When I spoke last time, nobody had, the word mega constellation hadn't been invented yet. But it's not only invented now, but it's growing like topsy. So this is thanks to Starlink, kind of got the whole thing going, SpaceX. Low Earth orbiting communication satellites are the darling of a whole bunch of corporate entities, but they are playing havoc with optical astronomy. Our colleagues who are running the dark energy survey with the telescope at Kitt Peak take pictures like this, which is the streaks from Starlink swarm that's on its way to its final orbit. And Lowell Observatory in Arizona is similarly plagued. You can see these nice galaxies there that are in the background. This is going to be a particular problem for Rubin, which has this wide field, so it's going to be hard to stay away from these tracks. You know where they're going to be, but it's going to be dodging them all night long as we try to accumulate this huge data set. The radio spectrum is, well, there's no mega constellations there yet, but there's plenty of interference, and what we're seeing in BMX is remarkable. All of these navigation satellite, these are constellations of tens or dozens of satellites as opposed to the tens of thousands that are likely to be plaguing the optical. But there's plenty of them. BMX has a field of view that's about 4 degrees right at the zenith. And we measure over one day, like a dozen of these navigation satellites passing over. So we have to kind of poke between their allocated frequency bands to get out data on sky. These are problems. Last topic. Rather than a mapper, we are also thinking about a mapper that can show us the distribution of matter in, we'll call it the modern universe. We've got an experiment called Lucy Knight that's under construction, which is to investigate the feasibility of measuring fundamental physics processes during what's called the cosmic dark ages. Here's that cosmic timeline again. This time I'm not showing you the size, the separation. I'm showing you what's in it at different times. Shortly after the Big Bang, things were very hot. They emitted light, just like a incandescent bulb, right? Things that are hot emit black body radiation. See that today redshifted into the microwave, cosmic microwave background. But after things expanded, and they expanded rapidly in the very early universe, things went dark. Things cooled enough to stop emitting visible light. Like it stopped emitting any electromagnetic radiation. And we entered this period called the Dark Ages, in which nothing existed but essentially clouds of cold hydrogen. And it's never been explored for the very reason that it doesn't emit any light. It's dark. After a while, so during the Dark Ages, there was still a coalescing of the hydrogen gas around overdensities, seeds of structure formation. And as they formed structures, they also, their kinetic energy, gravitational potential energy converted to kinetic energy, converted to heat, formed stars and galaxies. And the universe was full of light again. So basic timeline, first there was light, then it was dark, and then it became light again. And this period of the Dark Ages corresponds to the first roughly 100 million years, or until 100 million years after the Big Bang, which can provide very interesting information about dark energy, the seeds of dark energy, which wasn't really active then, but was hibernating, let's say, and the dark matter, which was interacting with this hydrogen gas at this time. It's never been observed, and we're going to try to observe it, or at least try to investigate the feasibility of observing it. Theory says, so keeping in mind the previous graph of redshift versus time, this is what theory says. Apparently these predictions are very robust because not much was going on. It's a bunch of cold, dark hydrogen, and dark matter interacting. There's no astrophysics. So the theorists love this as a laboratory. They think they can predict things quite well. And there's a feature called dark ages trough. It's very, very faint, and it has a redshift range that corresponds to a frequency range that it's mostly covered by what an amateur radio ham would call the high frequency band. The high frequency band is where that dark ages signal lives. But we're going to have problems observing it from the ground because that high frequency band has allocations to this many communication services, if you can believe that. I can't count them, and I don't think I have enough pixels to even read them. So we're polluting this part of the electromagnetic spectrum big time with our communications, with all of our devices. It doesn't help that the atmosphere is also noisy at these, in this band. We've got aurora, lightning, all of this makes things very noisy. And even if we could shut down all this interference, we have an atmosphere problem again, a different one this time. So if we go back and compress this into wavelength, this was the atmospheric transparency again. And remember, I showed you that for hydrogen out to redshift 6, we've got a nice open window. But for hydrogen at redshifts 40 to 200, the ionosphere is what gets us here. It reflects, it's electrically active. Electromagnetic waves of this wavelength excite the plasmas. There's all kinds of time-dependent phenomena. We really couldn't get decent measurements. There have been essentially no measurements of dark ages hydrogen from the Earth. The ones that were done were very, very sketchy. Coming to the end. So what Lucy Night is, so the L in Lucy Night stands for lunar. So we have a partnership with NASA to build a small radio receiver. Hard to call it a telescope. And it's not intended to do mapping. There's nothing to map. This is the dark ages. Things were just smeared out everywhere. But it's a spectrometer. We want to see this line and how bright it is at various look back times, looking hopefully for that dark ages trough. So we, as I said, we've already got a landing site picked out. This is a picture of the far side of the moon, and the yellow line is the anti-meridian. So as you know, the moon is tidally locked to the Earth, and along this line, the Earth is directly behind the moon. This is a great thing because the moon will shield us by a factor of over 1 billion from all the garbage and pollution that's on the other side of the moon, right? Big piece of rock, and it's electronically absorbing. It would sit on a ridge. We already have a landing site picked out. And at all times, it will block radio interference from the Earth. During the night, however, it will also block radio interference from the sun, which has its own radio characteristics. Now, this is the dark side. This is the far side of the moon. The moon no more has a dark side than the Earth does. It's commonly this common misconception, right? Here's what happens if you put Lucy Night on someplace on the moon. As the moon rotates around the Earth, it continually faces away from the Earth, but doesn't face away from the sun except when it's over on this side, right? So that's where the night in Lucy Night comes from. It's a lunar far side observatory that will take most of its data during the lunar night, which is as quiet as you can get. And so how are we getting there? NASA has a program called Commercial Lunar Payload Services, which is largely intended to foster the growth of space commercial industry. And so the way it works, they solicit proposals for payloads. Who wants to put a scientific instrument somewhere on the moon? And after a payload concept is given the go-ahead, they then go out to bid, and they have 14 companies that are bidding on basically delivery service, a ride share to the moon, and a lander that'll put you down where you say you want to be. So we have we've already been given the go-ahead. We're pre-manifested on a CLPS mission they call CS3, which you can look up and see the details. It's supposed to launch in the first half of 2025. Any day now, we will find out the result of the bid competition and who's going to give us our ride share. We'll start interacting with them to, tell them how heavy our payload is and so on, and want it to be. It's a simple enough payload. It's got an antenna. In these wavelengths, we don't make dish antennas. We make basically wire antennas. It's going to be a metal rod, 4 of them, that receives radio waves from outer space. Very good low noise amplifier. We've digitized things. After they're digitized, everything happens in digital logic. It's a computer that will live inside this box, make analog signals into spectra. Another complication of being on the far side of the moon is how do we get the data back? So we're going to need to do it in 2 hops. There'll be an orbiting relay satellite, which will actually launch on the same payload as Lucy Knight. At the moment, that's the plan. So that's going to be in orbit. We're going to observe during the lunar night, not talking to the satellite, because that would be another source of interference. And after the sun comes up, so we have all this data stored in a giant hard drive, we will wait for the satellite to appear in range, beam that data up to the satellite. It'll sit there for a while until the satellite goes around to the other side of the moon. It's orbiting the moon, right? And then send things down to Earth. There's some details here, but let me not take too much more time. I want to, okay, we have a collaboration with another lab, this time it's Berkeley Lab, also in California, and University of Minnesota, and the Berkeley Space Sciences Lab. This project got started in the first of 2022. And we have basically 27 months to get this payload ready to go to our rideshare partner, as opposed to the 25, maybe 27 years of Rubin development. So it's a crash program. It's really tough, working very tenaciously to get first prototypes working, hopefully within a few months, and then quite soon switch over and build flight model. And first quarter or first half of next year is when it's got to get delivered. They integrate it then into their lander, and the lander is integrated into a booster, and March 2025 is the tentative launch date. Last thing to say, we know, and we've got all this great publicity from JPL and others, that there's all these rovers, robotic rovers running around on Mars. There's been half a dozen of them in the 21st century, right? So they're coming thick and fast. They're coming rate of about 1 every 16 months, and that rate's going to increase. And they're doing all kinds of driving. Why aren't we seeing pictures of rovers running onto the moon? Well, here's the graph, here's the chart that shows you how many robotic rovers have ever been on the moon. 3. 2 of them were at the early part of the space age, and they were Soviet Union, remarkably successful for their time. This is what they looked like. And then only in 2019 did we have the next rover. So after this, 40-year delay, another rover finally made it to operate on the moon. It's actually on the far side, so-called Chang'e 4. And the rover is named U22. Why have there not been more rovers on the moon? The moon, after all, it's on this chart here. You can see it's 100 times closer. Shouldn't it be easier to get things there? It's hard to get things to Mars. Here's the reason. Let's see if I can. So a lot of it has to do with the fact that the moon rotates so slowly. It takes a month to go around. So it takes a month to go from high noon to high noon. That means it's got 354 hours of darkness, as opposed to 12 on the Earth. And it turns out Mars has a rotation period almost the same as the Earth. So the planets, Earth and Mars, get bathed in sunlight for 12 hours and then in darkness for 12 hours doesn't lead to an enormous temperature range. Because Mars gets quite cold at the polar regions, but the moon gets colder. And during the day, because the moon has no atmosphere, it's baking in the sun for 14 days, it gets really, really hot. It's a tremendously harsh environment. Unlike the Earth and Mars, there's no atmosphere and there's no magnetic field. And so there's little shielding from cosmic radiation. So there's kind of 250 times the radiation dose that we get on Earth. And not that much more than Mars, but still more. So it's extremely harsh. And to solve these are big challenges. We have to build an instrument that not only works, has incredible sensitivity to radio waves, but can survive under these conditions. One of the biggest problems is how do we power it during the 14 days of lunar darkness? There are solar panels that we'll use to charge up a battery, and then we'll run on battery, but it's easier than it sounds. A battery that has the capacity to store enough energy to run our equipment over 14 Earth days is really heavy, and it's going to dominate the weight of this payload. Okay, there's what things might look like on the moon. You another picture of the instrument as we now envision it. The antennas are kind of compressed into these little cans, and they shoot out 3 meters long, and their signals go down to an electronics box. That's where all the electronics business happens, and this giant box in the back, that's the battery. So this thing is basically a battery with a few appendages. We've got solar panels across the top and also on the sides. We've got to be able to catch the sun when it rises, so we need a east and when it sets, we need east and west facing panels as well as top facing ones. And to get the heat out, we've got a radiator that's going to face south. We're in the southern hemisphere, so that faces away from the sun at all times. It radiates the heat out. All of these are tricky design. It makes the electronics almost look like the easy part. I don't want to say that though, because I'm doing it. I don't want to go into some of the complications on the science side, but we have another big issue, which is that faint as this signal is, it is also obscured by radio noise from our own galaxy, which we can, components of which we have to separate by all kinds of trickery, including making sure we have a field of view that crosses and goes away from the galactic plane, because so we'll modulate the noise signal from the galactic plane by doing this, try to subtract it out. It should be said though that it's highly unlikely that Lucy Knight will see the Dark Ages signal, but our point is to try this crash program, if you will, and it's also got a very low budget. If we can take advantage of this CLPS program that NASA is offering to make a first pathfinder, and hopefully it's followed up by more extensive lunar observatories. I didn't put a summary slide together because I've already taken up. I want to thank you for your attention, and I'm happy to answer any questions.
We did have, yeah, see, so there's a lot of catty stuff. So mic sounds voice activated, turns off pauses, all this stuff. So here's one from Nicole. The launch of the Artemis missions and the plan for a colony on the moon. I think that the completion of construction of this telescope is possible within a decade. How long do you expect this to take? Also, how do you plan to shield the telescope from astronauts? Could you possibly cover it with a mirror dome?
Yeah, these are a lot of good questions. So, NASA and the European Space Agency and the Chinese Space Agency all have plans to put human habitation on the moon. Now, Artemis is the U.S. first step for the U.S. There are some big problems that have not demonstrated feasible solutions. I mean, for the first problem is they don't have a spacesuit that'll fit women astronauts. So that's what's going to hold up. That may be the gating factor in holding up the Artemis 2 mission, which is the first one that'll be crewed. We have all these heat problems for a habitation too. The Apollo astronauts, it's kind of remarkable. how clever that program was, because they landed at lunar dawn and left not much more than a few days after. So they were not exposed to the lunar night, where they wouldn't have power, and they would have had to, and they wouldn't have a source of power, and they would have to spend a lot of power to heat their capsule. They wouldn't have been able to walk around outside. The spacesuits for the extravehicular activities that they conducted have a remarkable evaporative cooling system that kept them from getting too hot. It's actually an interesting question: is what's the temperature on a planet with no air, right? What do you consider the temperature? Temperature of the soil is one thing. What about the temperature of a person standing on the soil? There's all kinds of thermodynamics that had to be solved, and it just gets harder if you try to build a habitation that can be either permanent or staffed for a complete lunar cycle. But plans are afoot to do so. A question that might be asked is why? Why have human staffed stations on the moon? And another question that's interesting is what's the role of commercial players, and what's going to be the motivation for them to undertake purely commercial, non-federal programs to put, let's say, more relay satellites. They're talking about putting a GPS constellation around the moon. Gosh, we better get our cosmology, radio astronomy done before any of that starts hitting. It's going to be an interesting story to follow. I think there's demonstrations that they are coming up with in white papers, and I think there's a lot of technology development activity going on. And maybe we'll see people walking on the moon again after for many years. I was 13, I think, when those guys walking on the moon. All right, the next from Daniel, there's a question. You had mentioned that dark energy drove the lacy accumulations of mass into filaments, nice line, characterizing galactic space. Do these distributions show scaling behavior, fractal, and how does it relate to the gene's mass and the distances that have been invoked to describe cosmic micro background anisotropy? I'm the wrong person to ask for basically all of those. I don't believe that fractal behavior is found in this web, this cosmic web. It may look that way, but it's neither random nor fractal as far as I know. And so the concept of the gene's mass would have to be, you would have to fold in the dark energy piece to make that make sense. As I said, absent dark energy, this coalescing of matter into these filaments would have happened much sooner and much quicker, and it would have come out looking different than it does. And the last question from Richard online is, can you explain? Richard is asking a good question. I do know the answer to this one. And if the universe is expanding and galaxies are receding from one another, how is it possible for Andromeda and the Milky Way to be closer to one another? That's a good question. So cosmologists think of the universe in terms so much larger than the distance between us and M31. The explanation is that it's the fabric of space that's expanding. It's not two objects. Space shouldn't be thought of any longer as the stage on which physical processes take place. It's a thing in itself. Space is something that can stretch. It can vibrate. We have gravitational waves that propagate simply through the metric of space-time, and it can gravitate in a way. It can make this negative pressure happen. That's what dark energy is. It's a property of space-time. That's why dark energy is becoming more and more dominant, because the amount of dark energy is proportional to the volume of space. As the volume of space grows, the dark energy becomes more and more predominant. That's why we didn't see it in the early half of first half of cosmic history. We see it big time now, and people talk about the big rip that will happen when the universe expands yet further and yet faster. So I don't have a good answer to what's the best way to visualize the expansion of the universe, but it is not a contradiction that nearby objects, which are gravitationally bound, will come together. Another question that I get from the audiences that are too clever is, does it mean that the atoms are moving apart from one another inside of molecules, inside of matter? And the answer there is no. So it has to do a little bit with what we mean by the distance between objects, but more so on local scales, gravitational binding is allowed in this cosmological concordance model. Right. It's hard to make that camera work without a telescope in front of it, right? Basically, the trick was to use a pinhole projector. So there, without any lens, without any, it's a pinhole projector. First, it's a camera obscura. It's like the wall of your room with, you make a tiny slit in your window, you can see objects visualized, just the way Daguerre made it. I don't think I know that exact way of describing what I have heard is that impact on the moon, there are seismometers on the moon that are working. They can sort of, just like on the Earth, see the sound wave that propagate through the lunar regolith. Maybe that's what sound, and I guess what they're surprising length of time. Yeah, it's hit the moon all the time. It's called We Have No Idea. Jorge Cham and Dan Whitson. Oh, yeah? Okay, so you've already.
So thank you so much.
Thanks a lot.
And several of the members are going to be heading out for dinner to debate of whether it's Applebee's or the diner next door. But if you are interested, follow along.
No, the diner's
Well, you guys
closed, been
can.
closed for years. So thank you, everybody who was on the call. I hope the sound was all right. We had to do a little jury rigging here, but next time I think we'll have some space staff around to help us out. And we have this event. How are people going to be notified of the link for SOMR? Is it on? They have it online there, right? Okay. We have to send her at least the video that I did. You have to send it. So thank you, everybody. We're going to kill the Zoom. Clear skies to everybody, and take a look at the comet if you can about the end of the month before the moon gets in the way. There you go. We will. Here's the sample. Good. Hey, how are you? How's everything? You're not getting any shorter. How's school?
It's going well, yeah.
Good.
So we'll skip into sophomore.